Yes, hi. So today I'm going to tell you about layer codes, which is a new family of codes in 3D. And before telling, does this? Yes, okay. So before diving a bit more into the details, I'm going to tell you what stabilizer codes are in general. So imagine that you have a bunch of qubits and having a hard time switching the slides. Is that okay? Is that like, okay, I shut. Great. So one of your qubits might be corrupted by an error. And the idea of stabilizer codes is that you might perform a bunch of measurements, for example, like M0, M1, and some of these measurements might detect where the error is. These measurements are also called checks or stabilizers. And in our context, we'll limit ourselves to measurements that are either of X type or Z type. By that, I mean that they're made up of either entirely X operators or entirely Z operators. And very crucially, all these measurements have to commute with each other. Sorry. Good. Okay. Great. So the issue with doing measurements is that as you scale up your system size, doing measurements between qubits that are very far apart means that you have to entangle them, and that can take a while. So asymptotically, you're kind of limited to measurements that have a finite range. A natural question, a natural question when you observe that is, does this have any impact on the code's performances? And it turns out that, yes, locality restricts the performance of stabilizer codes. How is that? So there are like very famous bounds. You might have heard of them in this conference before. These are called the BPT bounds, and they give you bounds on the properties of codes that live in 3D. These codes restrict some parameters, which are n, the number of qubits in the system, k, the number of protected qubits, and the size of the smallest error that you cannot detect with your measurements. So these bounds, you have like a bound on the distance and a trade-off between k and the distance. Okay, so it might be the first time that you're seeing these bounds. Here's kind of what they look like graphically. So here's a figure. You have here the x-axis is log n of k. This y-axis is log n of d. And the shaded region here is kind of the range of parameters that are supposed to be accessible for codes that live in 3D. Natural question is, are these bounds tight? And for a long time, we didn't know if that was the case. The kind of like the first important example of codes that live in 3D is the Turing codes. Like they actually live in 2D, but like 2D is in 3D, so it kind of counts. Then we had the cubic codes invented by Ha in 2011. Then we had the welded codes in 2014. And like all of these constructions were kind of attempts to get a bit further out into this region. But they couldn't quite get there because of something called the square root n barrier. We had a really hard time creating codes, even non-local codes entirely. Like creating any codes that went above this kind of like threshold of square root of n distance was really, really hard. Great. So there was like in 2023, this changed a lot. There was a result by Portnoy that created codes that are very, very close to getting to this like optimal point. And finally, with our result, we get to this optimal point. So you might wonder, what about this kind of slope there of the bound? But like once you have these codes, it's actually really easy to slide up and down on this slope. Great. So layer codes, what do they look like? They kind of look like that. They're CSS codes. They have these parameters. So like this is n, this is k, this is the distance. You can compare them with the parameters of topological codes in 3D. They have something called an energy barrier. I'm not going to expand on what it is, but just know that it is optimal and the weight of the code is upper bounded by a constant, the degree as well, and they do saturate the BPT bounds, which is what interests us here. How do these codes work? So fundamentally, these codes are more a mapping from sparse stabilizer codes to 3D codes. And this mapping takes codes that have these parameters and maps them to codes that have n cubed qubits, k logical qubits, and d times n distance. When you input good LDPC codes, which by now we know that they exist, you then obtain parameters that saturate the BPT band in 3D. Great, so how do we build these codes? Before telling you about how to do that with qubits, I'm going to focus on the classical case because it's a little bit easier. And to tell you how we got to that construction, I'm going to talk a little bit about this really amazing, fantastic paper, Sparse Quantum Codes from Quantum Circuits. It hasn't gathered that much attention, unfortunately, but it's like a really amazing paper. And what they do in that paper is like they take sparse stabilizer codes and map them to 3D subsystem codes. I'm not going to talk about subsystem codes in this talk, but they do have this very interesting result where they take something that's sparse in an arbitrary geometry and manage to map it to something that's 3D local. This construction relies on a Clark Hamiltonian, and I'm going to talk a little bit about how this Clark Hamiltonian works. This Clark Hamiltonian, going to explain how they work on bits. This construction takes as input three things. It takes as input like the input code that you're going to make local. It takes also a pair-to-check matrix, which is essentially a list of the measurements that your code performs. And it takes a circuit that takes, that for any bit string u is going to output the syndrome of the bit string. It's essentially a list of the outcomes of the measurements that you've performed. Once you have all these ingredients, you obtain your Clark Hamiltonian and your new code. Great, so it's going to be useful to visualize how the circuit works. You have the data qubits, you have the ancilla bits, you perform some number of gates over some amount of time, and the first step in our construction is going to be that for every time step that our circuit runs for, we're going to add a new row of qubits, bits, sorry. So if it runs on m bits for t time steps, we're going to end up with m times t bits. Second thing is, what we want is the code states to live on this lattice. We want them to be history states of this circuit. To do that, we're going to define the checks that are going to enforce this condition. And the way we're going to do that is for every gate, we're going to implement a check such that this check validates if and only if the value of these bits here corresponds to the value of these bits acted on by this gate. This might look a little bit weird and unknown, but a very simple example is with the swap gate. So the swap gate would swap the value of A and C. It corresponds essentially to having a ZZ check between A and D, because whatever the value of A is, we want the value of D to be the same. And also a ZZ between C and D, because whatever the value of C is, we want the value of B to be the same. And kind of like the punchline of this construction is if you start with the input code being a good classical code and you pick the right circuit, then you get some good history states. And these good history states allow you to saturate the BPT bound for classical codes. There exists a BPT bound for classical codes in 3D. It can also be saturated, and you can read a bit more about these in these works. Great. Now, if you look at this paper for a bit longer and you stare at it, you realize that you actually don't need a circuit. For example, if you have a long-range ZZ check between like two faraway bits, you can simulate this check by simply implementing a repetition code between those two bits, and this is going to enforce your ZZ check as well. You can do the same with like a three-body term. If you have 3 bits and a ZZ check between these 3 bits, you can also have a repetition code in that section that is going to carry the value of that bit all the way down there. This value is going to be summed with the value of this bit, and then this sum is going to be carried down there to be summed with the value of this bit. So you're enforcing a ZZZ check. Same thing for k-body checks. The general insight is that you can take whatever k-body check you have and decompose it in that kind of structure. And the end result is that if you want to map a sparse code to a 3D, here like a 2D local code, whatever bit you start with in the original code, you can map it to, okay, you have a code, sorry, you start with a sparse code. This sparse code has m checks. Every bit you're going to map it to a m-long repetition code, and each of the checks are going to be mapped to that structure that I've mentioned before, so like this kind of like a long repetition code. And you end up with a local code that enforces the checks of the original code. Great. Good. How do we make this quantum? So there's like some parallels that we can make that are quite straightforward. The input classical code has m checks. The quantum code is going to have mx x type checks and mz z type checks. In the classical case, we mapped every bit of C to an m-long repetition code. In our case, we're going to map each qubit of C to an mx time mz surface code. The sticking point is kind of, in the end, how do we break down these long-range checks? It was quite easy to do in the classical case. How do we do that in the quantum case? We're going to use a technique. To do that, we're going to use a technique called lattice surgery. And to explain lattice surgery, I'll have to like talk a little bit, very briefly, about the surface code. So most of you know what the surface code is. I'm not going to dwell on it too much. The point is that it has 2 logical operators, a z going up and down, and an x going from left to right. And we're going to, since we're considering 3D local codes as our target, we're going to embed this code in 3D. That's quite straightforward, but just as a bit of notation, we're not going to represent the rough boundary. It's just going to look all smooth all the way around, but like just remember that this is a rough boundary, this is a rough boundary, smooth boundary, and so you have those z and x operators. Great, so as mentioned before, the classical construction was like, you have a ZZ check, you map each bit to a repetition code, and this check you can simulate it with a repetition code in the middle, kind of. What is the quantum equivalent? Well, lattice surgery gives you an answer to that. What you do is essentially you introduce a new surface code patch in the middle, and then you're going to modify some boundary terms here and here, and this whole thing, like the surface code patch plus those modified boundary terms, are going to allow you to measure the product of the Z logical here and the Z logical there, which means that you have essentially enforced a ZZ check on your 2 qubits. Great, and you can see indeed that the structure of your logical is also going to change. So here is what the X logical becomes. You see that now the only X logical that you have has to act on the 2 patches of surface code that you had. As an addendum, if you have a more combinatorial background, you might be a bit lost, but just so you know that this lattice surgery patch can be quite naturally obtained as a hypergraph product of these 2 codes. Sorry. Great, so now that we've seen that, we still have like a couple of issues to solve because we need to combine X-type checks and Z-type checks. The problem is that lattice surgery patches for these 2 types do not commute. So here you have like an anti-commutation, and there you have an anti-commutation if you have like a ZZ on those 2 patches and an XX on those 2 patches. And it's also not entirely clear how to do K-body checks. To solve these issues, we're going to use the language of topological defects. And to talk about topological defects, I'm going to talk a little bit about condensation. So for the surface code, it's quite known that it's syndrome. So the record of the measurements that are violated can be divided into equivalence classes. And the notion of equivalence here that we use is that a class of syndrome condenses if it can be created by a local operator. So for example, in the surface code, in its bulk, this E excitation, which represents an X-type operator being, an X-type measurements being violated, this cannot be created in the bulk of the surface code. This is impossible. What you can do though is create pairs of excitations. For example, this blue M-type excitation, which represents a Z-type check being violated, this pair can be created in the bulk of the surface code. Now, these rules can be bent by modifying the lattice terms in a region. And when you modify lattice terms, you create what is called a defect. So for example, rough and smooth boundaries are example of defects because you modify the rules of condensation. So at this rough boundary, you can create an E anion, and at the smooth boundary, you can create an M anion. And this understanding the condensation structure of your code is extremely important because it dictates how the logicals are going to behave. Another reason why this is extremely important is because once you understand the condensation structure of your code, you understand how to obtain stabilizers for it. So like at a rough boundary, you can create two E excitations, you can join them together. This operator does not create any excitation, so it has to be a stabilizer. So that also gives you a recipe to create stabilizers, or like to know what your stabilizers are. Great, so now that we've introduced this kind of language of topological defects, we're going to review lattice surgery as a topological defect. To do that, we're going to introduce some abstract notation. This dot is, called the dot defect. It condenses these anions, and this cross defect condenses these anions. And you can see that this boundary here corresponds to a dot defect. So if you take your lattice surgery patch and you play around with your anions or like excitations, you can see that it obeys these rules. So yeah, this boundary is a dot defect. And by analogy, you can see that the whole lattice surgery patch corresponds to this representation in terms of cross defects and dot defects. And you can see that, yeah, like even creating a logical operator obeys this condensation structure. Great, now we can use the same insight as we had in the classical case, where we can take this cross defect and break it down into essentially a series of repetition codes-ish. This gives us a recipe to implement k-body checks. So you, if you have a k-body check, you can break it down into like this string of cross defects. And this gives you like a long surgery, lattice surgery patch with like certain boundary terms when it comes into contact with the lattice with the surface code patches that it interacts with. Great, and because we have this abstract topological defect language, we can also derive whatever the stabilizers are supposed to be. Now the last thing we have to resolve is how to recover commutation in these codes. As I've mentioned before, when you have these X-type and Z-type lattice surgery patches, they do not commute. What you can do is when you have two checks, so like here you have SZ and SX acting on the same qubits, you're going to pair up these qubits in a certain way, and between the qubits that are paired, you're going to introduce a new defect. So what is that defect? This defect corresponds to this combination of dot defect and cross defect. And it has this funny property where essentially it allows, if you didn't have this defect, you could have excitations that could go from here to there and create an error. And this defect not only repairs commutation, but also doesn't allow this kind of logical error to creep in. Similarly, we can also, from this abstract topological defect language, we can also derive whatever the stabilizers are supposed to be. So for that. Great, so maybe like a nice way to recap is to see how this construction applies to Shor's code when you take Shor's code as an input code. Each qubit of Shor's code is going to be mapped to a surface code. And then you can take the Z-type checks of Shor's code. These are going to map to lattice surgery patches. You do the same thing for X-type checks here in blue. And finally, you repair the commutation relations with these dull green defects. Yeah, so when you do that, you have certain properties that I've mentioned before. And now I would like to talk a little bit about the open equations that we have in our paper. The kind of like most important question is like, can we make a quantum memory out of these codes? Because we have a really, really good energy barrier. I would like to draw your attention though that having a good energy barrier does not imply that you have memory. So you have to be careful about that. The second interesting question, I think, is can we have more combinatorial formalism for this whole construction? Because like this is very condensed matter-y, very physicsy. Can we reformulate that in the more usual LDPC language, for example? Also, the way that we obtain the boundary terms for the defects is very ad hoc. It would be nice to have a more systematic understanding of how to obtain these terms. Something that I do find very interesting as well is this construction is like essentially a big machine that reduces the degree of your Hamiltonian as well. And something that is particularly striking to me is if you look at Eridiner's proof of the PCP theorem by gap amplification, the kind of like first procedure that you need is that you need to be able to reduce the degree of your Hamiltonian, right? And this is kind of what we do here. You start with an LDPC code that has like an arbitrarily large but fixed degree, and you end up with something that has like some very well understood degree. And can we generalize this construction to like Hamiltonians that do not commute, for example? And future direction, how to generalize this construction to higher dimensions, and how to perform operations and decoding on these codes has been left as an open question. That's it. Thank you so much.
Thank you for the nice talk. Are there questions? Is there a mic? Just behind you.
Oh. Yeah, thanks for the wonderful talk. Does the base codes that you use in the construction potentially inform anything that you could use for decoding the layer code?
Yeah, right. So the intuition kind of is that you should be able to first decode your surface code patches, and then you could use the structure of the top code to correct that. And you can very probably do that. It's just we didn't have the time with like QIP's submission deadline to do that.
Okay, fair enough. Also, if you're looking for a self-correcting quantum memory, do you think, can you use these codes to like reduce the number of encoded qubits so that there's only one logical qubit? I think it might be easier in that case to show self-correction than when you have k logical qubits.
Yeah.
Because even a 1 qubit self-correcting quantum memory is open in 3D. So
yeah, that would be great. I think actually it's kind of hard to get good LDPC codes with a low rate, right, surprisingly, right? Because like, so I actually don't know how you would do that, but that could.
Yeah, it wasn't obvious to me either. That's why.
No, that's a very good point.
But it seems like it would be easier to prove that it's self-correcting if you could do that. So there's some tension.
Wow.
Oh, thank you.
There's another question over here.
Thank you for the very nice talk. So you mentioned a lot of elements in the construction of layer codes, say lattice surgery and topological defect condensation. And I'm wondering, or can you give a little recap of how these elements are necessary or how they work so that this layer code construction saturates the BPT bound? Thank you.
Yeah, so the recap is essentially that with these defects, you preserve essentially enough of the structure of the original code to have, sorry, I'm looking for a slide. Yes, to have these parameters. So like regardless of the input code, you'll always get n scaling as this, k scaling as that, and d scaling as this, where mx is the number of x-type checks. And when you input a good code, so you have k scaling as n here, and you have d scaling as n here, you can compute all that and see that it does match the optimal parameters for the BPT bound.
So are trying to design a code construction protocol so that you can have these forms of giving you the input parameters, you get these forms of output parameters, or you just start with the construction and you find that you have these input-output relation so that you satisfy the BPT bound.
Sorry, could you repeat?
Yeah, so it's kind of, do you first have the idea of how you construct the code using these elements, or you're trying to design a protocol that give you specifically these input-output relations?
Like how did we come to this construction?
Yeah, so suppose you want to design another set of relations. You input some parameters of input codes and you get the output codes parameters. And is there a universal way of designing a construction protocol so that you can do it? Or you just started from the construction and you find these relations?
So could you get like a different relations for these? Right, so like a really good different construction you could get is if you didn't worry about 3D locality, for example, you could have these surface code patches be really, really, really small and how do I want to put it? Okay, so if you had these surface codes become really, really, really small, what you'd get is the density of qubits would really increase, but like if you don't worry about 3D locality, that's okay. And essentially you end up with something whose locality is really close to the original code. So like the parameters would vary only by a constant, but you would have managed to reduce the degree of the original code to a constant that you know. So like in that case, these parameters you would, because the size of the surface code patches would be much smaller and would be much smaller as well, and you wouldn't get these these parameters there.
Okay. Maybe we can leave it there, and if there are more questions, you can ask at the lunch break. Let's thank our speaker again.